Hello everyone, welcome back. Congratulations, you made it this far. You completed chapter 1 and we're now about to start chapter 2, which is all about the two-body problem. So what is the two-body problem? Well, the two-body problem is a theoretical situation that doesn't exist in practice, in which we assume that all we have at play is two-point masses attracting each other. So in our situation, we would assume that one of those two masses is a planet or a gravitational primary body, and the second mass would be our spacecraft orbiting around it. So again, all there is are two bodies interacting with each other. One is the planet, the other one is the spacecraft. Okay, so this is the two-body problem. So let's dive in. Chapter 2. Two-body problem. Now, obviously, this situation doesn't exist because in practice, there is the sun's influence, there's the moon's influence, there is the influence, gravitational influence of all the other planets in the solar system that are pushing and pulling our spacecraft as its orbit around the planet. But again, to begin with, we'll assume that all we have is the main body about which our spacecraft orbit. Okay? So first thing first, we're going to have a look at the basics. Okay? And within the basics, the first thing we want to do is to derive the two-body equation of motion that will allow us to predict or to solve the motion of a spacecraft on orbit. So we're going to call this section relative equation of motion. Now, the reason why I call this section the relative equation of motion and not just the equation of motion is because the motion of our spacecraft will be measured relative to the planet. Okay? So, let's assume that we have 2 point masses, say M1 and M2 over there, and that their position as seen from an inertial reference frame like that. So the positions are denoted capital R1 for the position vector from the origin of that reference frame all the way to M1. And let's move M2 over here so that we can better see those two position vectors. And R2 vector denoting the position of M2 with respect to the origin of a truly inertial reference frame. Okay? Furthermore, let's denote R, small r, as the position of M2 with respect to M1. So let's draw small r from M1 all the way to M2, like that. So head-to-tail summation will tell you that R1 plus R is equal to R2, or in other words, that R2 minus R1 is equal to the position of M2 with respect to M1. Or in other words, the relative position of M2 with respect to M1. This is what the small r denotes. So in that section, our objective is to obtain an expression for the acceleration vector of R2 of M2 with respect to M1. And this is why this is called the relative equation of motion. Okay? So, this is the position. We can also look at directly taking the double derivative, inertial derivative, of that equation like that. So the inertial, because this is the solid dot notation, the inertial acceleration of m2 with respect to m1 is r2 double dot minus r1 double dot. All I did to go from here to here is taking the double derivative, or the second time derivative. Okay? Let's keep that in our back pocket for now. We'll come back to that expression later on. So what we're going to do now is to look at the inertial acceleration of m1 with respect to the origin of that inertial reference frame that we drew previously on the board. Okay? And then we'll do the same thing for m2 in terms of its inertial acceleration again, but this time with respect to the origin of this reference frame. What do we know about those two accelerations? Well, Newton's second law, as we said in the previous chapter, told us that ma is equal to the net force being applied onto the mass. What is the net force being applied onto m1? Well, this is the attracting force as exerted by m2 on m1. Okay? So this is F12 vector, like that. I'm gonna write it in red. F12. Again, this is the attracting force applied to m1, but caused by m2. So this is that force that causes m1 to be accelerated. Okay? And similarly here, we have the inertial acceleration of mass 2. This one caused by the pulling action from m1. Like that. And this is F21. F21 like that. Okay, so this is the generic application of F equal ma in this very simple situation. But can we quantify those two forces mathematically? Well, the answer is yes, obviously. Otherwise, I wouldn't be asking you. Okay? Yes, we can, because we know that those forces are due to the gravitational attraction. So in that case, we can apply Newton's gravitational law to quantify F12 and F21. F12 is in the same direction of our position vector r that denotes the position of m2 with respect to m1. So we know that there is no minus sign in front of it. So g m1 m2 are vector over the distance cube, where here I've used just the symbol r to denote the norm of my position vector. So r is the distance between m1 and m2. This is just the length of that position vector r. So this is F12, but going back to my diagram here, I can say that F21 is in the opposite direction of my position vector r, and thereby I need the minus sign here. Okay, so minus g m1 m2 position vector, right? F21 the opposite direction of r. All this being divided by the distance cubed. Okay, that wasn't too bad. Now, going back to those two equations we just derived, we can simplify those by dividing both sides with m1 and m2, those two equations respectively, like that. So we end up with inertial acceleration of m1 with respect to the origin of my inertial reference frame equal to the universal gravitational constant, the 6.6 blah 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 I told you last time, times m2 times position vector over distance cubed. And I can do the exact same thing for the inertial acceleration of point mass number 2 with respect to the origin of my inertial reference frame here. And this is being equal to minus g m1 position vector divided by distance cubed. And the reason why I've been able to apply those equations to this situation is because this is truly the inertial acceleration I'm looking at. Okay? And again, Newton's second law, F equal ma, is only applicable in a truly inertial reference frame. All right. So this is what I have here for R1 and R2 double dot. But previously I had obtained this very simple equation here. Okay? So what I'm going to do next is just to take those two expressions and substitute them into this equation here, which is R double dot, or in other words, the inertial relative acceleration of m2 with respect to m1. Or in other words, how does m2 accelerate with respect to m1 as seen from an observer sitting on this inertial reference frame? Well, it's not too difficult. It's just plug and play. R2 is my minus g m1 position vector over distance cubed minus this expression I have, which is g m2 position vector over distance cubed. Now, obviously, I can take my universal gravitational constant out of those two expressions. I'm going to say minus g times m1 plus m2 times my position vector, which is also applicable to both terms. All of this divided by distance cubed. And this is for the inertial relative acceleration of m2 with respect to m1. Okay. If you focus your attention on this last expression, you should notice that we have this particular term inside those parentheses, which is the summation of m1 and m2. Now, generally speaking, this is valid, but in the situation where we have m1 being a massive planet and m2 being our spacecraft, S-C is going to be my abbreviation for spacecraft from now on because I'm a bit lazy. Okay? I'm not lazy, that was a joke. Well, maybe I am, but I won't tell you. Okay? So the mass of a planet compared to the mass of any spacecraft is much, much higher. So therefore, what we're going to do from this point on is to assume that m1 plus m2, the summation of the planet and the spacecraft orbiting around it, is going to be approximated to be the mass of the planet only. And that leads us to write small r double dot equal to minus g m1 times position vector over distance between m1 and m2 cubed. Now this is very convenient because that tells me, going back here, and now if we again assume that m2 is a spacecraft orbiting around a planet, it tells us that the spacecraft acceleration with respect to the planet is not dependent on the spacecraft mass at all, which is a very particular situation. And the reason for that is that the difference in masses involved is so large that we've been able to make that assumption. Furthermore, it tells us that this expression is also only function of the position vector between m1 and m2 through the position vector r and also its distance, but also function of g times m1. G was our universal gravitational constant that we spoke about last time. And m1 will be the mass of the planet about which the spacecraft happens to be orbiting. So if you assume that m1 is also a constant, then I'm going to group those two constants together to write, instead of minus gm1, I'm going to write minus mu. And our vector over distance cubed like that. And mu is a very simple parameter to practically determine for astronomers and scientists, which I'm not, I'm just an engineer, right? So it turns out that this constant is somewhat easier than G on its own to measure accurately. How to do it, I have no idea. This is beyond my head, okay? But the beauty of it is that we don't need to know the mass of the planet practically. We don't know to remember the universal gravitational constant value for G. All we need to know is what is the mu for the planet of interest, okay? Mu is known as the standard gravitational parameter and is unique for a given planet. All right. So if you look at the lecture notes, the PDF document, on table 2.1, I have listed for you all the standard gravitational parameters for all the bodies in our solar system. So you have mu of the Sun, mu of Mercury, Venus, Earth, Moon, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. Although Pluto isn't technically a planet anymore, yet I felt that Pluto deserved a row in my table. Okay. So as long as you know about which planet the spacecraft you're trying to determine the acceleration is orbiting about, you just plug and play that constant value for the planet of interest, and boom, that is going to give you the acceleration experienced by the spacecraft while it is orbiting about the planet. Okay? So this particular equation has a name, and this is the well-known two-body equation of motion. And I would say that this is the first very important equation in this course. Okay? If in 5 years from now all you remember from this course is that equation, I'd be happy. Well, not happy, but I won't be disappointed. Let's put it this way. Okay? So the two-body equation of motion allows us to predict or to calculate at any given time, based on where the spacecraft is with respect to the planet, through this position vector and through this distance scalar here, what acceleration is it experiencing. Furthermore, once you've calculated the acceleration at each time step of the process, you could go and integrate this value at each time step to obtain the velocity of the spacecraft on orbit. And then integrate again to get the position of the spacecraft at each instant while it is orbiting. Okay, so in other words, it's very simple. Okay, it doesn't get any simpler than that. So this very simple equation of motion allows us to completely describe an orbit. If you are familiar with MATLAB Simulink, I think you are taking a course, or you took a course in the past, 3600 SISC, which is System and Simulations, something like that. So you have in Simulink a block scheme diagram. So you have the main script here that would calculate the acceleration based on the current position vector and the current distance between the spacecraft and the planet. That would give you the current acceleration with respect to the planet then what you need to do is to integrate the signal once to get the instantaneous velocity vector of the spacecraft, and integrate that signal again, 1 over s is an integrator, to get the position vector at each time step. Okay, position vector of the spacecraft with respect to the planet. And here you could have a box that takes the norm of this vector, spit out the distance, and then you feed both the distance and the position vector inside this block. Recalculate the new acceleration 1 time step ahead, integrate again twice, get the new position vector, get the new distance, feed this back, and so on and so on. And then if you were to plot the x, y, z components of this position vector on a 3D plot in MATLAB Simulink, you would see an orbit. Okay? 3D plot in MATLAB. Now, the catch to that is that, well, how in hell are you going to initialize the two integrator blocks? So in other words, what would be the initial velocity t equals 0, and where are you starting the integration process in terms of position? Are you starting here along the equator? Are you starting somewhere over Russia, South America? Who knows? That would be your initial position at t equals 0. And now what speed are you traveling at that initial instant? Not only what speed, but in what direction, because you remember that a vector has both a magnitude and a direction. So are you traveling straight up, somewhat inclined, perfectly horizontal, as if you had an equatorial orbit? So this is through the careful selection of those initial conditions that you will be able, as an engineer, as a designer, to generate any types of orbits. Is it an equatorial orbit that you're trying to visualize? Is it a polar orbit? All of those things solely depend on those initial conditions. All right, the rest here, the minus u is just a constant. The position vector is only a byproduct of the integration process. So as the three parameters that you can play with to generate a given type of orbit, again, all you have to do is to carefully select those two sets of initial conditions: initial position vector and initial velocity vector. Okay? Now, selecting those two quantities is not a trivial process. It could be very complex. Turns out, instead of selecting those two vectors in 3D space at t equals 0, we're going to select or specify a set of orbital elements. There are 6 of those. Okay? Based on those 6 orbital elements that you would specify, there will be a routine that would allow you to convert from orbital elements, OE, up to initial velocity at t equals 0 and initial position at t equals 0. And then you feed those two signals to your integrator blocks, and then you start the integration process. That's a hands-off process at that point. It's closed loop, so it would generate the position x, y, z of your spacecraft at each time step. Okay? The way to go from orbital elements to R and V at t equals 0 will be seen later down the road in this chapter. The definition of our 6 orbital elements will also be seen later in the chapter. So everything will be covered, and you will get a chance to practice this on your own by playing with the MATLAB Simulink software that is available to you on CLearn, and that is part of the assignment. Okay? But then you may say, oh, isn't that more complex? Because now we have 6 parameters to select to generate a given type of orbit we are looking to analyze. Whereas here, all we had to do was to select 2 parameters. Well, no, because again, any vector has a magnitude and a direction. So this has 3 entries to it. X, Y, Z, and that one, 3 entries as well. So regardless of if you go through the process of selecting 6 orbital elements, converting them into position velocity at t equals 0, or just starting right away from position velocity at t equals 0 without having this extra process here, you will always have to select 6 parameters to initialize any type of orbits. And the reason for that is because an orbit evolves in 3D space, where you have position and velocity, both of those in 3D. Okay? So X, Y, Z components for position, X, Y, Z components for the velocity. Okay? So all of this was kind of a parenthesis on the side to highlight the powerfulness of this very simple yet very elegant equation of motion. Okay? And the reason why this is called the two-body equation of motion is because in practice, not only you have the gravitational attraction created by the planet on your spacecraft, and this is done through the mu parameter, but in practice you would also have additional perturbing acceleration, FP vector, due to drag, due to solar radiation pressure, due to the non-sphericity of the Earth, right? The Earth isn't a perfect sphere, the Earth is kind of an oblate shape, and that creates deviations or perturbations from the perfectly spherical model, which is inherently assumed when we use the two-body equation of motion. Okay? But for now, just remember, I want you to remember that equation on top of your head. This is, again, the most important, or one of the most important equations of this course. So r double dot is minus mu times r vector over distance cubed. Okay? All right. So let's keep moving forward. The next subsection. So you see that we are already building upon the blocks that we've covered in chapter 1, right? We have looked at Newton's laws, and then we've just applied them blindly to our situation where m1 is much greater than m2, and boom, equation of motion of a spacecraft around the planet. Okay. Next thing to look at in 2.1.2, we're still within the basics of the two-body problem, which is in 2.1. In 2.1.1, that was a two-body equation of motion, that equation that predicts the acceleration of our spacecraft on orbit. In 2.1.2, we're going to have a look at some fundamental integrals. Or in other words, 3 things that are not going to move at all if we consider that all we have is a planet attracting a point mass or a spacecraft towards it. Okay? There's no other influence. All we have is those 2 bodies in space. Or in other words, those fundamental integrals, or things that are not going to vary with time, are only valid under the two-body problem assumption, which is, again, a theoretical situation because in practice, there are other planets affecting the spacecraft motion, but there are also perturbations, as I just said, drag, solar radiation pressure, tidal effects, gravitational perturbations due to the oblateness of the Earth, and so on and so on. So just keep in mind that those things that aren't going to change with time are only applicable under this theoretical assumption. So the first thing that isn't going to change at all, or the first fundamental integral, is the angular momentum. Or in other words, angular momentum conservation. So what we're going to do first is to formally define our angular momentum vector h. Can you see that well on the screen? The marker is becoming dollar as we move forward through the lectures. I'll have to buy a pack of those, I guess. Anyway, so angular momentum is h. So we're going to say this is not any angular momentum, but the orbital angular momentum, which is equal by definition to the position vector cross product with the velocity vector of our spacecraft. Okay? From this point on, small r vector will always denote position of m2 with respect to m1, or in other words, the position of the spacecraft with respect to the planet. V here is going to denote the inertial derivative of our position vector, or in other words, the velocity vector of m2 with respect to m1, or again, the velocity of the spacecraft with respect to the origin of our primary body, m1, the planet. Okay? And if you look closely at that equation, you realize that, hey, there's no mass again involved in the spacecraft. And this is why, technically, this is in the orbital angular momentum, but rather the specific orbital angular momentum. I'm going to call h as specific angular momentum, orbital angular momentum, just angular momentum throughout the course, and I'll always refer to h, okay? But through various wording. So if our objective in here is to demonstrate that the angular momentum of our spacecraft on orbit is conserved, well, guess what? We'll look at taking the derivative of that expression. So we're going to have a look at h inertial derivative equal to, well, all I do now is that I'm going to take the chain rule and apply it to the right-hand side of that expression. I'm going to say that this is our inertial derivative cross v plus the first one cross product the derivative of the second one, v dot. Okay? So next, I'm gonna focus my attention on that one, let's say, to begin with. So I'm just going to write the first term as it is, r dot cross v plus position cross. What is v derivative, inertial derivative of my velocity vector? Well, obviously this is my inertial acceleration. Acceleration of what? Acceleration of m2 with respect to m1. Right? If this is r, then the derivative of r is my velocity vector of 2 with respect to 1, and such that v dot is my acceleration, or I'm going to say double inertial derivative of my position vector. It's all the same. Do we know at that point with what we could replace this inertial acceleration of m2 with respect to m1? Do we have an expression for that? The answer is yes. And what is that expression? You should know on top of your head by now. And this is your minus mu position vector over distance cubed. Because we're not talking about any arbitrary acceleration here, but we are specifically talking about the two-body equation of motion, or the acceleration created by the gravitational attraction of m1 onto the spacecraft, m2. Okay? Oh, that's interesting, because if you look carefully at that expression, you realize that what you have on the first term is r dot cross product. What is the velocity vector in terms of r? Well, this is r dot again, plus we have minus mu over r cubed here as a scalar times r cross r. And hopefully you didn't forget already the definition of the cross product of two vectors. Okay? So a cross product of a vector with itself will always give you 0? No, the null vector, right? Cross product of a vector gives you a vector. So here you get the null vector for this first term plus a scalar. Look at what we have again. Another cross product of a vector with itself. Null vector plus null vector equal to null vector for what? Null vector for h inertial derivative. And that is the very proof that our angular momentum for a spacecraft orbiting about the primary body isn't changing with time. Or in other words, that the specific orbital angular momentum of the spacecraft on orbit is conserved. Okay? Because h dot is equal to 0, that means that my orbital angular momentum h is equal to a constant under the assumption of the two-body problem, right? Why do I say that? Well, because in this demonstration, when I substituted my acceleration of my spacecraft for the two-body equation of motion, this little equation, and everything here I assumed that I was talking about the two-body problem because all there is here is the gravitational attraction of M1 onto the spacecraft through the mu factor there. So I didn't replace v dot with this plus some external perturbing acceleration due to the moon, the sun, other planets, due to drag, solar radiation pressure, and so on and so on. All I had was a very simple two-body equation of motion. So this is why the conclusion I got at the end of this derivation is only applicable under those assumptions. Okay? So always remember that under the two-body assumption or the two-body problem framework, the specific orbital angular momentum of the spacecraft is constant or is conserved. That is the takeaway here. Now, what is the implication of that? We'll have a look. The implication is the following. So let's first remember what was our h equal to r cross v. So say you have your planet, the Earth here, and the spacecraft orbits around it. A big orbit like that, highly highly elliptical orbit. Okay? If you have, at that point in time, switch marker because this one is dying on me. Hopefully this one works. If you have at that point the position vector of the spacecraft r, and you happen to have the velocity, say, going down here, so the orbit is going counterclockwise around the Earth like that, that is the velocity vector. What you have to realize is that when you take the cross product of r and v through the right-hand rule, you'll always get a vector which is perpendicular to both vectors involved in the cross product. Okay? So r cross v will give you a vector which is normal to r and normal to v. Okay, this is your h vector going down. So if r and v are actually drawing a plane, because two vectors could be drawn on any plane, right? It's only a matter of tilting the plane properly to catch those two vectors. And if h is perpendicular to the plane and is known to be constant, what it means is that the plane of motion, so imagine a 3D plane, it's going to get messy thanks to my highly refined drawing skills. right? That's a plane in which the orbit evolves, and that is the plane in which both r and v vector exist. It means that by virtue of the conservation of the specific orbital angular momentum, that this plane is constant and doesn't tilt around as time goes on. Okay? We're going to say that the plane in which r and v exist is constant, because this vector, which is perpendicular to the plane, is constant. If that vector, which is kind of attached to the plane of motion, would be moving around, it means that the plane in which the spacecraft would evolve would also tilt and move. But that's not the case. Okay? H is constant, and so is the orbital plane, because that plane in which r and v exist has a name and is known as the orbital plane. It's constant. I'm going to say due to h dot equal to the null vector, or due to the conservation of specific orbital angular momentum. And that plane is the orbital plane. Okay, so that is the practical implication of conservation of angular momentum of a spacecraft. So I said there were three fundamental integrals. The first one was conservation of angular momentum. The first one we're going to have a look at is conservation of orbital energy. Well, before that, let me take a sip of my green tea. And that will be, did we have a section for conservation of angular momentum? I don't think so. So I'm going to say the integral is the orbital energy, okay? I'm going to say conservation of. All right. So same thing as before, we have to derive and to mathematically prove that the energy of our spacecraft is constant throughout the orbit. Or in other words, that the orbital energy is being conserved. So how are we going to do that? Well, the first thing we're going to start out with is our two-body equation of motion. That's mu, distance cubed, position vector. So what we're going to do in this first step is to take the dot product on both sides with r dot. There is no particular reason to do it this way. There are multiple ways to prove that the orbital energy is being conserved. But I find that this process I'm about to show you is a really neat one. Okay? So that first step of taking the dot product with the velocity on either side of that first equation is not something you are expected to determine on your own, but just try to follow the steps as I go along and make sure you understand all the derivation, okay? You will never be asked to demonstrate that on your own without any hints or clues on how to do it. So let's have a look at this left-hand side of our two-body equation with which we took the dot product with r dot. Well, it can be shown, well, it will be shown, where this dot product r dot is equivalent to taking half of the time derivative of r dot with itself. Okay? If you're not too sure if that makes sense, well, you can try out the right-hand side here and see if it works. So if you have r dot, and you do the time derivative, you're going to get chain rule, r double dot, plus r dot product, r double dot. Or in other words, you're going to get 2 r double dot product, r dot. But that's not what we had on the left-hand side because of the factor 2. So if you do 1/2 on both sides of that equation, then we get 1/2 d dt of r dot product, r dot, and 1/2 here is going to indeed give you 1/2 d dt of r dot product, r dot equal to r double dot product, r dot. And that was a lot of dots, okay? That was a lot of dots. So that's why we are allowed to say that. Or in other words, you can say that this is 1/2 d dt. What is r dot? This is your velocity vector dot product itself. Hopefully you remember from chapter 1 that a dot product of a vector with itself, because the angle between those two vectors happens to be 0 degrees, all you have is magnitude of the first one times magnitude of the second one, right? Because cos of 0 is 1. So you have 1/2 d dt of your speed squared. Speed again being the magnitude of your velocity vector. Okay? So we're going to go back to our original equation and replace. No, we're not going to replace it now, but we'll just say that this is also equal to 1/2 d dt of speed squared. I'm going to leave it like that for now. So I'm going to keep that equation up on the board because we're going to go back to it eventually. So next, we're going to say that if we have r dot product r, and we know very well that this is equal to distance squared between m2 and m1 because this is what r denotes. Now if we take the time derivative on both sides of that equation, we're going to get d dt, position vector dot product with itself, equal d dt of distance square. Now applying the chain rule on the left hand side here, we're going to get velocity dot product position plus position dot product velocity, like that, equal to the time derivative of this is going to be 2 times r, and the derivative of whatever was to the power 2. So that's just the speed, okay? So here, the velocity vector dot product position vector plus position vector dot product velocity vector means that because the dot product is commutative, the order with which you do the operation is meaningless. So those two terms then are exactly the same, okay? We're going to come here and say that you have 2 r dot r product r dot product r equal to whatever we had on the other side, 2 distance times speed. You can cancel the 2 and say that velocity dot product position is equal to distance times speed. All right, let's keep that in our back pocket. This is an intermediate result. Now what we're going to do now is take the time derivative of 1 over r. Why the hell? Because that's the process to demonstrate that energy is being conserved. Okay, you never have to pull this thing from your hat. That's not something you are expected to be able to do on your own. But here, just bear with me through the process and make sure you understand why things are being canceled and why we could apply this to that and so on and so on. Okay? So if you take the time derivative of that, you're going to get minus 1 distance square times the speed. This is another intermediate result, if you will. Why? Well, because if you go back to our original equation, we had already taken care of the left-hand side by replacing this with that. Now we're going to see what we can do with this right-hand side of that equation. The minus mu over r cubed, our vector dot product with velocity vector. Well, we have just established that position vector dot product with velocity vector was equal to distance times the speed. So let's replace that. I'm going to say such that minus mu r cubed position vector dot product velocity vector. That is my initial right-hand side of my starting equation here. Now, by virtue of that, I'm going to rewrite it by minus mu r cubed. I'm going to replace this dot product that I have here with r and r dot, which means that I can cancel my r and write minus mu over r squared times the speed. And look what we have from this other intermediate result we have just gotten previously. We have minus 1 over r squared times r dot equal to this. Minus 1 over r squared times r dot. That's exactly what we have. The only difference is the factor mu. So I'm going to further rewrite that as being equal to minus d dt of mu times 1 over r, or just divided by r. Okay? So now we've been able to completely rewrite the right-hand side of our starting equation differently, like that. Okay? Just by virtue of playing with equations and things that kind of made sense to us, the derivative of that is equal to this, and just doing some tricks here and there. Okay? I'm going to go back to what we did initially. And again, what we did was to take the two-body equation of motion and apply the dot product of the velocity vector on either side of that equation, the term in red, essentially. And now I'm going to replace this with minus d dt mu r. So that entire expression now becomes 1/2 d dt speed square equal, where did the minus, what happened to my minus? Did I screw up the minus sign? Yes, so that was correct. So minus this is this. And we have minus mu you probably all see it and you're laughing because I can't see where did I miss the minus sign in the process. So minus mu, so r dot is this. We did that. So we had minus mu r dot. Okay, it's because here the minus r dot over r squared is the positive derivative. So minus here is my positive derivative. Whew. Positive derivative. It's going to happen a lot because there's no one to help me out in class. Just, hey Steve, you forgot your minus sign. Okay? I'm on my own in my basement, essentially. So I have to troubleshoot myself often, probably, because there's just a ton of equation in that course. So equal to then positive on that side, d dt mu over r, which means that I can take the time derivative out of everything and write that this is time derivative of speed square over 2 minus mu over r. I'm going to say that this is equal then to 0 because I took this term and flip it on the other side of that equation. And now if you look at what we have here, the objective of that section was to demonstrate that the orbital energy was conserved, or that was constant, implying that its derivative was equal to 0. So the derivative of something is equal to 0 here in the end. So surprise, surprise, this proves that the time derivative of the orbital energy is equal to 0. Or in other words, that the orbital energy is being conserved. And that is good news. Okay? Because that's what we wanted to do. So just by looking at that, then we could infer that the orbital energy of our spacecraft is then equal, by definition actually, to speed square over 2, that's your 1/2 v squared that you all know about, minus mu over r. Essentially that makes a little sense because this is your kinetic energy on orbit and this is your potential energy. So the summation of those two energies, so summation of positive kinetic energy and summation of negative gravitational energy or potential energy, sums up to the net orbital energy of a spacecraft orbiting a planet. But it's slightly different than what you're used to because it's massless. For this reason, the orbital energy, in that case, is known as the specific. Not specific, but specific. Specific orbital energy. Okay? Key result. Not only this, but the fact that d dt of the orbital energy is equal to 0. This is what we've established here. And again, this is only valid for the two-body problem because in the process I have used a two-body equation of motion, and in fact that was the starting equation. R double dot equal to minus mu times r vector over r cubed, which is only applicable for the two-body problem because there are no additional terms that would come quantifying the effects of other planets and other perturbations on the motion. All we had was M1 attracting M2 through the mu scalar there. All right? So what is the implication, the practical implication of that? Well, that's a big one. Because if the orbital energy is to be conserved, it has to hold at any point along an orbit. Okay? So this is an orbit seen in a plane, and this is M1. So that's the plane of motion, or in other words, this is the orbital plane. I'm not sure if you can see that properly. It's a little faint. Let me mix in some red. Essentially, this is the path of the spacecraft around M1 in the orbital plane. So again, the orbital energy being conserved has to hold at any point along my orbit. Okay. So again, M1 is the Earth, and the spacecraft is orbiting in this direction, like that. So the orbital energy has to be the value at this point, but that value has to be exactly the same at the farthest point along the orbit, which means that as r which is the distance between M1 and the spacecraft. By the way, that's a spacecraft with 2 solar panels. Great drawing skills, I know. Thank you. So that distance between M2 and M1 is small here, but large over there. This is R, at 2 instants. If you look at the definition of the orbital energy, it means that the speed has to vary greatly too. Because if this gets smaller, to ensure that the orbital energy is conserved at any point along the orbit, it means that the speed has to be quite large there, but quite small over there, and varies in between, okay? So this is the implication of the orbital energy being conserved. So R and V are being scaled up and down, inversely proportional to each other, to ensure that the net orbital energy stays exactly the same at any point along the orbit, including the closest point, which is known as the perigee of the orbit, and at the farthest point, which is known as the apogee of the orbit. Perigee and apogee are just Latin names that are used generically, regardless of the planet about which a spacecraft is orbiting about. In a case where M1 happens to be the Earth, the perigee is going to be known as periapsis. Periapsis. And the apogee is going to be known as apoapsis. But throughout this course, I'll only refer to those 2 specific points of the orbit as perigee and apogee, okay? Just because that's what I'm most comfortable with, regardless of the planet. All right, so this is for the conservation of a specific orbital energy. That was the second fundamental integral. Let's move on to the last one, which is the eccentricity vector integral. Okay, so again, there's no section numbering for that. So we're still within 2.1.2 fundamental integrals, and the third one being the eccentricity vector. Okay? So again, the process starts from someplace. You won't have to determine that yourself. But let's just have a look at what would happen if we were to take the velocity vector cross product with the specific orbital angular momentum vector h. And specifically if we were to take the time derivative of this quantity. Well, obviously, if you apply the chain rule to that, you would get v dot cross product h plus v cross product h dot. Right? This is exactly what you would get, just applying blindly the chain rule to this term. But if you're clever, you'll probably remember that h dot is equal to the null vector, correct? We're still within the 2-body problem assumption here. And we have demonstrated up front that our specific orbital angular momentum vector was being conserved, or was time varying, it's the same thing. So then we're going to come back here and say that this is v dot cross product with h only. But, hey, we know what is h equal to. I gave you the definition. So v dot cross product, what is our orbital angular momentum? Well, this is simply the position vector cross product the velocity vector. That was the very definition of the orbital angular momentum. Now, if you look closely what we have here, we have one cross product and second one. Turns out that this is the triple cross product for which we have an identity. Remember in chapter 1 I said at one point we're going to use some identities. I'm not going to bother writing them on the board. They're listed in equations, whatever. And this is one of those instances where we're going to come back and replace those cross products with an equivalent that uses dot products, okay? And if you are interested or if you care, we are specifically talking about equation 1.21 in chapter 1, which is the identity that we're going to use to go from this to what I'm about to write. So v dot product v. That gives me a scalar. Remember, dot product of two vectors gives you a scalar. A scalar, I can easily multiply that with a vector that I can do. Minus v dot product position vector times my velocity vector. Again, this is what I use to go from here to here. Now what I'm going to do is take a sip of green tea because I'm thirsty today. And green tea is so good. Okay. So we're still looking at d dt of v cross h. We're just playing with the right-hand side of that equation. Okay, so I'm going to come back up there and keep playing until I find what I'm looking for, which in this case is to prove that the eccentricity vector, which you don't even know what it is going to be constant, or that the rate of change of that eccentricity vector is the null vector. So if you look at that equation, we have the v dot term here and there. What is v dot? Well, again, this is our inertial acceleration. And we know that our inertial acceleration is our two-body equation of motion, correct? That's our minus mu times position divided by the distance cubed. So I'm just going to substitute that expression for my v dot terms in that equation and see what we get. So minus mu position over distance cubed, all this dot product with velocity, and all this being multiplied with position vector, minus, again, minus mu position r cubed. This is for v dot, then dot product with r, close the parenthesis, all this multiplying the velocity vector. Like that. Okay? Now, what I can do from that point is to focus on what I have here. I'm just going to write the first term as it is, minus mu, position vector, distance cubed, dot product, velocity vector, times position, minus. We have a dot product of a vector with itself. Position vector dot product with itself gives you r square. I'm not going to explain again why. If you're not too sure at that point, I would highly recommend you go back to chapter 1, our foundational chapter. But because I have minus minus, I'm going to say this is plus mu over r times my velocity vector. And just for completeness for the time being, because I have mu here and mu there, I'm going to take it out. I have mu, velocity over distance, minus position dot product velocity over r cubed. And this multiplies my position vector, and I can close the big parentheses just like that. Okay, all I did from here to here is to pull out the mu from those two terms. We're going to keep that in our back pocket, so I'm going to write that expression over there so we don't forget what we're doing. Plus h. We know that this is mu times v r minus r v r cubed. All this times r, and close that parenthesis. Okay? So, what we're going to do next is to take the ratio of position vector over distance, and furthermore take the time derivative of that. Why? Because that's the process of showing or proving that the eccentricity vector is being conserved or is time independent. Okay? Again, you won't have to know those steps that seem to be coming from nowhere. But again, what is important is to be able to follow through the intermediate steps, how to go from one equation down to the other one by substituting, say, with the two-body equation, by performing those dot products, those cross products, and understanding what is most important here, I guess, is understanding the implication of things at the end of the derivation. Okay? So, well, this is equivalent of saying that this is d dt of r vector times distance to the power minus 1. And the reason why I wrote it this way is because of ease to play with. So, chain rule to this, and to give me position vector dot distance to the power minus 1. Then plus, but because I have, well, you can just write it, plus this. Now time derivative of r to the minus 1 becomes minus 1 in front of it. So minus 1. And then r to the minus 2. And then the derivative of what we had here, which is r dot. I'm going to write this expression slightly differently by recalling that r inertial derivative is my velocity vector of the spacecraft with respect to m1, this is v, over distance between the spacecraft and the planet. And here, I'm just going to pull the r square on the bottom. So minus position vector times r dot over r squared. Now, from before, we know that r dot r was equal to position dot product velocity vector, right? I believe we looked at that in the second fundamental integral. We had established that relationship. So I'm going to make use of it here by replacing my r dot by position dot product velocity over distance. Okay? I'm going to just say that this is velocity over distance minus position with r squared. My r dot is going to be replaced with position vector dot product velocity vector over r, like this. Or in other words, write this as velocity vector over distance minus r inertial derivative here is your velocity vector. So I'm going to say position dot product velocity over r squared times r on the denominator. Denominator becomes r cubed, and all this multiplies position vector. Okay? Now, this is quite interesting because out of nowhere, we had just established that this is equal to that. Or let me use a different color. You'll understand why in a second. And this side was equal to that. But just from before, we had also established that this was equal to this. Aha! Quite interesting, isn't it? Because if you look at what we have in the red boxes here and there, this is pretty much the exact same result, except there's a factor mu, which is different. And that leads us to say, by virtue of the fact that red here divided by mu is equal to red there, it means that this divided by mu has to be equal to this. Okay, so I'm going to say d dt v cross h over mu. You can pull it in front of everything because that is a constant. Okay, is equal to the other green boxes, the other green box, d dt position over distance. Ha! What was our main objective in that section? Does anyone remember? I didn't hear, but I assume that the answer is yes. The objective was to prove that the time derivative of the eccentricity vector is 0, or time derivative of a given vector is 0, because we don't know quite yet what is the eccentricity vector. But here we have essentially the time derivative of v cross h divided by mu minus position over distance equal to the null vector. So the time derivative, I'm going to erase this because this is getting not too clean. Okay, so the time derivative of a given vector, because this is a vectorial operation, right? Cross product of two vectors gives you a vector divided by a scalar. It's still a vector. And same thing here. You have a vector divided by a scalar. So what you have essentially here is a subtraction of two different vectors. Time derivative of that giving us the null vector. And boom, just like that, we have achieved our objective of that section, which was to demonstrate that the time derivative of the eccentricity vector was 0, or the null vector rather. Which, from that last expression, we can then infer that the eccentricity vector, denoted by E vector, eccentricity vector has to be equal, and it is equal by definition, to velocity cross product orbital angular momentum over mu minus position vector over distance, which means that we have indeed achieved the objective of showing that the eccentricity vector was the third fundamental integral of the two-body problem, or in other words, that the eccentricity vector alongside the orbital angular momentum and the orbital energy is being conserved. Okay? So, as we did for the first two, let's now have a look at the practical implication of that very important result. So now that you know how to calculate the eccentricity vector based on velocity, orbital angular momentum, and position vectors? Well, you need to know something more to be able to fully appreciate the implication of that key result. I'm going to use so M1 planet. I'm going to draw the orbit in red as before. Okay? So that's the orbit. And M2 being our spacecraft, actually orbiting around in that direction. This is one full orbit as seen in the orbital plane. So in the plane in which position vector r and velocity, which is tangent to the orbit instantaneously, are collocated. Okay, so those two vectors are inside the plane. We have established that that plane of motion is not moving around because the angular momentum, which is perpendicular to the plane, was conserved. So it doesn't move, so the plane doesn't move. And so the plane in which r and v evolve as time goes by is also constant. We have also established that as the distance gets smaller here at the perigee, the speed must increase, and vice versa at the apogee, when the distance increases between M1 and the position of our spacecraft, as it is directly there, while the speed at that point must decrease to ensure that the net specific orbital energy is being conserved at any point along the orbit. That was the second implication. And the third one is this, right? The eccentricity vector is not moving. Well, you need to know that the eccentricity vector is a vector that starts at M1 and always points at the direction of the perigee, which is the closest point between the orbit and M1. So I'm going to write it for you. Eccentricity vector always points at the perigee. Right? And this is key because although we had established that the orbital plane didn't move in 3D space, it is standing still. In that example, we could pretend that the orbital plane is the whiteboard. So the orbit is seen in that plane. The board is not tilting around in 3D space because of the orbital momentum being conserved. But the fact that this specific vector is frozen in space, right? E dot, or the rate of change of that vector, is zero. It doesn't move. It is set in concrete, set in stone. It means that because it's always pointing at a specific point of the orbit, it means that that orbit is also not moving in the orbital plane. Because otherwise, if the eccentricity vector would have been allowed to vary with time, if say we would have eccentricity vector derivative different than the null vector, then that would have meant that this specific vector, eccentricity vector, would be allowed to shift and sometime down the road pointing up. But because this vector always points at the perigee, that would mean that the perigee later on would be here or all of a sudden there, which would mean that the entire orbit would be allowed to rotate in this orbital plane, which is the whiteboard. Okay? But now because this vector is fixed inertially, that just sets the orbit to also be inertially fixed in the plane. Okay? So again, to summarize, the takeaway of the fundamental integrals concept is that the orbit in which, or the plane in which the spacecraft evolves around M1 is set in stone. And you could pretend that this is the whiteboard plane. Second thing is that position and the speed have to be scaled accordingly to ensure that the net orbital energy, which is your v squared over 2 minus mu over r, that quantity is constant throughout the orbit. And this is why we see the spacecraft accelerating or decelerating throughout the orbit. And finally, we have established that this orbit, which is drawn in red, is not rotating around M1. It is set. Okay, so everything is inertially fixed in terms of the orbit and its orbital plane. So that concludes today's lecture. Hopefully that kind of shed some light into the scope of work we're going to be doing throughout the semester, because what we did today was to begin with first principle and then derive a bunch of equations together to arrive at net results that would give us some insight into the practical implications of things and as to explain the why. Okay, why is the orbit not moving around if there aren't any perturbations pulling on our spacecraft? Well, because we know that for the two-body problem, the orbital plane is constant by virtue of the conservation of angular momentum. Why is the orbit not rotating about M1? So in other words, why is the perigee always pointing over Russia? Well, that's because we have established that for the two-body problem, the perigee was inertially fixed. And that in turn was setting the orbit to be inertially fixed. Things like that is going to become our bread and butter for the remaining of the semester. And again, there was nothing dramatically new here. All we're doing is using our building blocks that we've derived in Chapter 1 and using them or assembling them in different ways to get a better understanding of spacecraft orbital mechanics. Hope you enjoy this lecture. Hope it makes sense to you. And keep looking forward to more videos. See you soon, guys. Bye.